Good evening, everyone. My name's Steve McNeil. I'm a senior scientist in the building performance team at BRANZ in New Zealand, so that's the Building Research Association. So I'm going to talk to you about our trends in air tightness, predominantly in residential buildings in New Zealand, and some of the work we've been doing in our research programs to help support change as we go through. So today I'll give a quick overview of the New Zealand climate for all the people internationally, so they get a bit of a view of the type of environment that we live in, as well as the regulatory framework and what that means with regards to air tightness. And then we'll take a short look at the trends and drivers for air tightness in the New Zealand context. And then alongside that, I'll also bring up some of the recommendations that exist out there in industry. So there are some from BRANZ, there are some from external organisations that are trying to drive change. So we'll cover some of those. And then I'll get to where we think things will need to go in the future in this space in New Zealand. So we've had a couple of crises over the decades with what's been termed the leaky building syndrome, which is very much like what Canada experienced in the 1990s. So we have an industry that has some particular challenges to get over when it comes to robustness of our buildings, and you'll see some of these things shortly. Okay, so to give you an idea of the climate in New Zealand. We're located just southeast of Australia, and it's predominantly Köppen CFB climate, though parts of the South Island do get into the colder DFB in a few areas. So what that means is we have quite mild seasonal temperature swings, but our climate is reasonably humid. And some of those colder areas in the south, for example, that I was talking about in the sort of DFB kind of climate classification, they're about half the absolute humidity of what we get in parts of the North Island. So, there's some particular challenges we have when it comes to dilution ventilation, and that kind of plays out in some of the things you'll see as we go through tonight. Next slide. Okay, so compliance. What does compliance look like in the context of New Zealand? Well, it's actually, we don't actually have a regulation for air tightness. So we have a performance-based building code, and I've borrowed this image here from the regulator, where it kind of lays out the structure of that. So we have a Building Act which was passed by Parliament, which is then underpinned by a building code, which creates a set of objectives and functional requirements that buildings need to meet and performance criteria. And then the next part of that is the compliance pathway. How do you demonstrate that your building meets these requirements of the building code? So that next layer down in the pyramid there, we're talking about alternative solutions, or verification methods, or acceptable solutions. There's some of the pathways you can use to demonstrate compliance of your building with the building code. So there's a few clauses that actually are quite closely related to air tightness. So we're talking, obviously there's energy efficiency, but we also have our ventilation clause, the G4 there you can see on the left. Indoor moisture is a particularly challenging one given our humid climate and the fact that we don't necessarily heat our homes that well. And then B2 durability is also another concern. Obviously, if we have a building that is too air leaky and there's a lot of moisture passing through those air leaks into vulnerable spaces of the building, there's the opportunity for that moisture to condense and end up causing a whole raft of mold and decay and all those kind of issues. So that's obviously something that we're very keen to avoid. So in terms of what the Building Act says there about air tightness, it's literally those three words there at H1.3.1b. So a building envelope has to try and limit uncontrollable airflow. Now, in the rest of the entirety of the acceptable solutions and verification methods, there is no definition of what constitutes uncontrollable airflow at present. Though there is a comment in the latest edition of the energy efficiency clause for the building code, or the acceptable solution for the energy efficiency clause of the building code. And you can see that there in the lower box, number 2. So measures should be taken to limit the amount of moisture that can migrate from occupied spaces into the roof or roof space. So that primarily came about from very, very strong trend in New Zealand to use downlights in ceiling diaphragms, and we were effectively relying on the interior lining as the air barrier. Obviously, once you start using recessed downlights in those sort of locations, you're punching holes in your air barrier, and if the downlights themselves leak or the fitting around them leak, that can lead to quite a significant amount of air and moisture flowing across the ceiling, and that has led to quite a few issues with moisture in roof spaces. There are other causes as well, but this was a recognition of the role that air tightness has in helping to avoid some of these issues. Okay, so let's dive a little bit into what we actually have in New Zealand at present when it comes to air tightness. So we've got a reasonable air tightness database that goes back to the early days when Mark Bassett was involved with the AIVC. So we've got a database of several hundred buildings, which is just being collected as part of research projects. Since we don't have a large air tightness testing industry, that's what we've had to rely on up until now. Although we do see an increase in the numbers of testers in New Zealand, mainly driven by people's membership to voluntary schemes. But I'll quickly run through the trends over the decades and talk through sort of the changes to our building stock that have led to these changes. So on these graphs that you can see here, they're just a histogram of the makeup of our database for the different ages of buildings. So obviously left-hand side of the plot is the percentage of the sample that sit in that group that sit in these individual little buckets of air tightness there. So you can see there from the Group A buildings, the ones earlier than 1959, nothing was tighter than 6 air changes at 50 pascals, for example. And you can see they do get quite leaky up to 22, 23, 24 at 50. So as we go through the decades, though, once we get into the 1960s, we start to see a trend that gets pretty evident shortly. So 1950s and they tended to be, there's a lot of old stock that went back into the 1880s, for example. They tend to be strip floor, they tend to be suspended floor construction, so not concrete on grade. Because we have earthquakes, the predominant method of construction for a long time was suspended timber floor. So as we go into the 1960s, though, you can start to see there's a little bit of a tightening up of the distribution, and a lot of that is due to changes in building habits that happened. So there wasn't actually a driver for improving air tightness. It just kind of happened as we changed the way we put our buildings together. So once we get into the 60s, you start seeing strip flooring starting to be replaced by sheet flooring materials. Might seem like a small change, but when you have like a perimeter leak around a floor because you've had to leave room to get the last floorboard in, and all of a sudden you don't need to do that because you've got a continuous sheet, that does make quite a difference to the air tightness that you get. So if we now jump to the 1970s, that's where that really starts to embed. So you can see we're now getting buildings that are in the 3 to 4 air changes, 50 pascals kind of range. Obviously, there's still some pretty leaky ones, but that trend continues. So as we go through into the 80s and 90s, which you'll see shortly, but as we get into the 80s, we start to see the timber joinery starting to be replaced by, unfortunately, it was all non-thermally broken, but aluminium joinery. So that actually had seals that worked a lot better than a majority of the timber joinery of the day. So that itself started to improve the air tightness of our buildings. So then you fast forward a little bit into sort of the 1990s and early 2000s. So this is an era where we were starting to see a lot more larger scale development. Group home builders were doing a lot more buildings, and sort of insulation and energy efficiency was starting to become things that were focused on a lot more. So you can see here we're getting to see quite a lot more of a trend towards more airtight construction. And in that period from the sort of early 1990s through to about 2005, we were getting into the thick of some of those leaky building issues that I mentioned earlier, but it also coincided with trends to plaster cornices being used and different methods of lining and detailing the interior linings of buildings. And that tended to create these more airtight structures by default, because the house buying public were demanding higher levels of finish quality. That high level of finish quality kind of flowed through to the kind of result that we were getting. So you can see there, even in the early that group F there, 2000 to 2010, there's quite a strong peak around 6 at 50 pascals. So that's sort of showing that we are getting this consistent trend. The other thing that I probably forgot to mention was that around the late 70s, probably mid 70s actually, we were starting to see a lot more concrete slab on grade construction, and that's really flowing through into these results here. So all of a sudden, we may have had a situation where we've replaced that strip flooring with sheet flooring, and now all of a sudden we have slab on grade. So that's effectively impermeable in the center of the building, unless you've got a particularly interesting slab. But it does mean that we've lost a lot of that leakage opportunity. So it's a good thing from an airtightness perspective. Obviously, around the edge of the slab, we've already got issues with how do you detail the timber bottom plates and things like that. So present day, this is where we're currently sitting from the last measurement campaign that we did. I think it finished about 2014, 2015, so we are getting a little bit out of date now. But what it kind of shows is we are getting, the majority of new builds are getting sort of below 5 air changes at 50 pascals, kind of by accident, which is a good thing, but ideally would like to see some more consistency, which kind of leads me nicely to the next couple of slides. And obviously you can see there's still some variability there. We're getting some places up around 10 air changes at 50 pascals still. And if you, I think my experience with those was they tended to be the most architecturally interesting buildings, but not necessarily the simplest buildings. So as the complexity of the building goes up, obviously the opportunity for these kind of extra linkages to occur happens. So all of those slides are kind of summarized in this chart here that covers off most of our database up until the present day. So you can see the box and whisker plot showing the extremes, and then the shifting of the means and distribution of that sort of in a kind of two quartiles in the center there. So it's been quite a steady bit of progress, though there are some challenges that we have. So in terms of recommendations, so BRANZ as a whole, we have a recommendation out there as a blanket one of ideally trying to achieve at least something below 3 air changes at 50 pascals, backed up with including mechanical ventilation. The reason for that is we've done quite a bit of research work looking at the typical leakage pathways in your average building. So we have a few test buildings on site where we've effectively gone through and documented as we've made them more airtight, looking at where the different leakage opportunities are. And in order to get from a typical, one of the buildings, for example, started off at 14 at 50 pascals, we got it down to, I think it was 3 or 4 quite easily. But we documented all the different things we did. So there are a number of quite simple measures that we have been encouraging industry to kind of adopt. So that would be things like sealing bottom plate junctions to floor slabs as being a quite important one, and other really simple ones, like there's a common habit of recessing the edge of the lip of a bathtub into an external wall or showers or things like that. And just a simple thing like, fitting a lining behind that before you go and do that kind of recessing, or building it out slightly and creating an air barrier at that point before you fit the bathtub. Because those quite large holes are quite significant leaks, but they're very, very easy to fix if you do it at the right time with quite simple guidance. So that mirrors a lot of what you see coming out of some of the, I think it's Build America and a few of the other programs in the US. I think reaching out to the builders from a quite practical perspective has quite an easy payback when it comes to improving what people do. So we've found sort of case study approaches as being a really powerful way of getting some of these things across. With that being said, regardless, we do have an issue in that we haven't really ventilated our homes that well for quite some time. So we already have problems with indoor moisture and the like that are tied to a number of issues around the way our buildings are put together, especially our older stock. And although we shouldn't be saying you have to ventilate just because you're building more airtight, I think the fact is we need to ventilate better regardless. So that's why our recommendation that exists out in industry is stressing to include mechanical ventilation as well as being more airtight, because it kind of deals with two particular issues that we have. And I mentioned the older building stock before. To give some context, around about 50% of our building stock currently was built before 1980. And if you saw what those graphs look like, that's quite a significant amount of stock that's going to be quite leaky. So we have a bit of catching up to do in some areas, and it's actually a really good opportunity because a lot of those homes aren't actually that energy efficient. So the windows are poor, the levels of insulation need updating. So it's an opportunity to actually improve a lot of these things all at the same time. Let's jump to the next slide. Yeah, so this kind of reiterates the statements I was making before. Simple, affordable changes to current building methods should get buildings below 3 at 50 quite easily. One of the other reasons why we've got 3 as a pragmatic target is we've done quite a lot of work with gas tracer measurements and coheating measurements in some of our test buildings. And what we've seen, particularly in our pretty mild climate, is that there is a bit of diminishing returns. So although you can save more energy going down to 2 or 1 or even getting down to sort of pH kind of levels of 0.6, there are other bits of the building envelope that are more impactful when it comes to improvements. Not to say that aiming for better isn't as bad, and I don't think it is. It's just the case of 3 is a sensible, pragmatic number that can get the most people starting to do something. I think what we find is if we set something to be too high a limit for industry to adapt to, it tends to turn people off. So you have to start them in that journey and progressively improve it. So I mentioned roof space moisture earlier. So where we have these kind of ceiling down lights, and that line that was in the acceptable solution for the energy efficiency part of our building code around making sure that the ceiling diaphragm was reasonably airtight. These images on the right here are the sort of problems that we see in our roof spaces. So you can see 2 different building underlays there. One that's got a whole pile of condensation on it, and the lower one obviously has quite a lot of mold on it. And these are the kind of things that we see quite regularly, and it's the sort of issues that we have to be quite wary of. And it's not just airtightness that can help solve these. Obviously, improving ventilation equals improving how much we heat our homes. All those kind of things can help with some of those issues. So I've got a little slide here saying the future. So if we look at what we currently do, we have testers who are reporting numbers in both air changes per hour at 50 pascals, but also in the permeability metric, the cubic meters per square meter envelope per hour at 50 pascals. Given our relatively humid climate, we're probably going to be along the lines of mirroring what's happening in Australia and some other parts of the world, where the permeability metric may be the more useful one for setting a particular limit. And the main reason for that is that if we're using a permeability limit, it becomes a much easier task to assess hydrothermal risk with tools like WFI. So we can look at the air permeability of the wall assembly as part of that equation. And obviously we can simulate an air leak into an assembly and say, right, well, how likely is that to cause a particular problem? So it becomes quite an easy thing for us to justify saying, well, we need to just pick a particular permeability limit based on the results of some hydrothermal modeling, because of the diminishing returns we see from the energy perspective. It's going to be a much more appealing thing for industry to use air tightness as a means to deal with the risk as opposed to energy cost. And that wraps up where I got to tonight, but thanks for the opportunity to talk about the work that I did with my colleague Manfred. Apologies I didn't give him credit at the start of this.